We're going to do the guided practice for static equilibrium. We're going to do, a series of problems. So we'll start with a sign problem. A shop sign weighing 512 newtons is supported by a uniform 115 newton beam as shown in the figure. A guy wire is attached to the attached 0.3 meters from the right end of the beam at a 28-degree angle to the 2.05 meter long beam. Find the tension in the guy wire and the horizontal and vertical forces exerted by the hinge on the beam. So let's work our way through this. Let's first finish labeling. Here's the sketch. I know this is the force of the sign, and that weighs 512 newtons. I have this tension force, right, that we don't know. We also have the beam, the pole itself, so I like to call this the force of the center of gravity, and you're told that the beam weighs 115 newtons. And then here there are two forces. There's a horizontal component of the hinge and the vertical component of the hinge. But we don't know those either. So here's the thing. How do I know that the hinge acts up and to the right? I don't. It doesn't really matter. If you put them the wrong direction, you'll get negatives for them. If they come out positive, you'll know you drew them the right way. If you get negatives for them, you know you drew them the wrong way. So let's also label our distances. So we're told that the total length of the beam is 2.05 meters. And that's, and this angle here, you're also given, this is 28 degrees. And this wire, this distance here is 0.3 meters. So you want to try to label all the information. I don't want to have to read this anymore. I go back and keep reading the problem over and over and over. So once I've got that, I can write out my equation. My equation is net torque clockwise equals net torque counterclockwise. And now I need to do sum up the torques. Well, which way is clockwise and which way is counterclockwise depends upon which way where I put my fulcrum. So I'm going to put my fulcrum here. Well, why do I want to I always show it with a triangle. Why do I put my fulcrum over here anyway? Well, because I have two variables at this point, and if I put my fulcrum here, those variables go away because you can't have a torque exerted at the fulcrum. So where you put the fulcrum is kind of analogous to when we set y equal to 0 wherever we want. So it's just kind of a nice thing to be able to do. Now you can move it, you could put it somewhere else, but this is the easiest way to do it. So that's why I did that. Now I need to also decide which way is clockwise. So the best way to do that is to actually take your pen and place it on your picture and rotate it in the direction, right? Like put your finger on the fulcrum and move your pen. So if you move it clockwise, you'll see that you'll be moving in the direction of arrows that go this way. This direction is clockwise. And this direction, any forces going in that direction, are counterclockwise. So clockwise one's first. So I'm going to have the torque from the sign, plus the torque from my center of gravity. Both of those are pulling down. And then I'm going to have torque from the tension from the wire, right? That one is pulling up, right? Is going in that direction. And again, these two don't exert any torques because they're at the fulcrum. So this is going to be the force of the sign times the distance of the sign. And this is a 90-degree angle, so sine of 90, plus the force from the center of gravity times that distance for the center of gravity times, again, sine of 90, that's here, equals the force of tension, right, that's my wire, times its distance, times, now it's not 90, it's 28 degrees. So let's put in everything we know. 512, the total length is 2.05, sine of 90 is 1, so I'm done with that. This is 115. The distance is the middle, right? This here is in the middle of this 2.05. So that's 1.025 meters. And sine of 90 is just 1, so I can ignore that. I want to find my FT. My RT, this from here to here, right, is 0.3 less than my total length. So that's 1.75. So now I've got everything except FT. So you can do the algebra out and you find you should get the tension force ends up being 1423.75 newtons. All right, so now what? Now I need to find these two forces. For this, I'm going to use the first law of equilibrium, which means I need a different free body diagram. I'm going to draw a free body diagram that looks like a point. This is what we did in chapter 4 or 5, right? All those. So I'm just going to take all of my forces, F of the hinge on the Y, F of the hinge on the X, FT, FCG, and F of the sine, and draw it all on one free body diagram. Now that I've done that, I'm going to break my FT into components. I have my X component, and I have my Y component, and I can get rid of that. So now I can do the summation of the forces. My net force on the X has to be 0, and my net force on the Y has to be 0. That's the first condition of equilibrium. So I've got on the X, F of the hinge, the X component, minus FTX has to be 0. So I'm looking for the X component. It's going to be FT times cosine of 28. When we know what FT is, because we just solved for it, times cosine of 28 gives me an FX of 1257 newtons. On the Y-axis, you have F of the hinge on the Y plus FTY minus FCG minus F of the sine equals 0. So you're looking for this. I'm going to move everything over to the other side, and you get FCG plus F of the sine minus FT sine of the angle. So we have all this, yep, 512 plus 115 minus 1423.75 sine of 28. And if you do that out, you get negative 40.3 newtons. And you should notice I got a negative for that, which means that this Y component really acts in the downward direction, not in the upward direction. So this is one of the few times when if you get a negative for your force, you need to be able to interpret what that means. So we've solved for all three variables. We used our rotation, right? Our static equilibrium for rotational and for translational motion. I just want you to know that you could do this using rotation and putting the fulcrum somewhere else. But regardless, you could use that to solve for F of the hinge on the Y, but you could never do it for the X component. And that's because it exerts no torque. So you can't use rotation to solve for this variable. So regardless, you'd still have to set up your free body diagram and do this equation. So that's how you'd have to solve it.